welcome to the third and last lecture on this topic, quantum thermodynamics and transport. I added also the word transport. Yeah, so the last lecture was about dissipation. It's a sort of sad story because it's the subject of investing work that is dissipated. So I tried to tell you how to describe it, but it was just about that. I think that today is more fun because I will try to discuss mechanisms in which you also have the effect of converting heat into work and the other way around. And so this is the typical, so the easiest situation. We talked about that in the first lecture in the context of thermoelectricity. This is a case where heat work conversion takes place in steady state. But the other very well-known situation where this effect takes place is in the usual cycles. And the paradigmatic example is the Carnot example. Here is the case of a heat engine when you have the evolution in four-stroke processes, two in contact with the reservoirs, a hot reservoir, a cold reservoir. In these two strokes, you have exchange of heat, and you also do some work, while there are also parts of the evolution. I think that these arrows are in the other direction, sorry. Yeah, they are in the other direction, so you have a cycle. This one is in the other direction. In these parts, you evolve decoupled from the two reservoirs. Here, it is given the name adiabatic. The adiabatic evolution here in classical thermodynamics, we use the name adiabatic to tell about processes which are very fast. Instead, in quantum physics, is the opposite. I forgot to stress that point. In quantum physics, adiabatic is attached to the idea of a very slow evolution. Okay, so these are these classical cycles are thought as processes which are quasi-static. In particular, these ones which are in which the system evolves coupled to the reservoir, I thought as a series of snapshots, like you freeze the system. It thermalizes with the reservoirs. With the reservoir, you change your parameters. In this case, you change the pressure. And okay, it's a quasi-static evolution, so you don't have any generation of entropy. So entropy in all the cycle is conserved. This is the change of entropy in all the cycle, and you have basically two exchanges in the two steps where you evolve in contact with the two reservoirs. Here, as a fact that after completing the cycle, you come back to the same state, you can also express this equality. And using these two equalities, you get this expression. This means that this work I'm using here to stress the fact, this conservative, to stress the fact that this is a work done as a sequence of quasi-static processes. This is the heat exchange from the hot reservoir, and you have this difference of temperatures divided by the temperature of the hot reservoir, which basically defines the Carnot efficiency. Okay, so this is the important term here. So this term tells us the fact that there is some heat work conversion. And we will recover something like that later in finite time processes. Yeah, in finite time processes, we want something which provides some power. So this sequence of quasi-static states take a very long time. So the period of that cycle goes to infinity. So you don't basically have power. So in order to get power, you need to do something which takes to implement these mechanisms in using some finite time processes. And this is what I want to discuss today. And yeah, before that, I want to mention that this story of studying cycles basically started in this paper. I think that the name of quantum thermodynamics started with this paper. This is an extremely simple calculation, but it was formulated with the idea of implementing the experiment. So one of the authors here is the experimentalist. And this experiment is done in a single ion, in the case in a single ion in a trap, in a Pauli trap, and the ion is basically modeled by just an harmonic oscillator with a frequency which can be changed. It is thought in terms of a 4-stroke process. I'm going to show you here in more detail. In one of the strokes, you only change the frequency. So these changes of the frequency can be implemented by deformations of the trap. So if you deform the trap, the ion can move in this direction, and as it moves in this vertical direction, it changes the frequency of its oscillation. So there is one process in which the ion changes the frequency, keeping some temperature, beta 1. Afterwards, it is connected to some hot reservoir. So this cold and hot in these ion trap experiments are implemented with different lasers, acting with lasers on the trap. And okay, but in the description of the experiment, you can think that it couples to a hot reservoir. So in the coupling to the hot reservoir, it is, so you see that the calculation is basically evaluating the initial and the final state of each of these processes, making the difference and just saying that this is in this case, the heat. So if you calculate, you say that you change here the temperature, you have the final value of the frequency, and you evaluate the energy at the final state minus the phi. It's an extremely simplified description. And the cycle is completed by changing back the frequency and then connecting to a cold bath. So in this procedure, it is argued that, okay, you can perform the cycle with a single ion, and you can get some work, and if this takes some time, it is simply divided by the period of the cycle. Okay. So, but this is the experiment. So the experiment is not so ideal because as you put in contact the ion with the different hot and cold reservoirs operating with the lasers. You also change the frequency, so it's something which is closer to a finite time cycle. Anyway, it is something which is close to that idea. And this was, I think, a very important proof of concept that you could implement this kind of cycles in the lab. Okay. So, yeah, these are the extreme simplifications in the description I presented before. It is assumed that there is in each of the strokes, there is a perfect separation in processes in which you just do heat, exchange heat, and in processes in which you do work. And it is completely neglected the fact that there are time-dependent processes in the switching on and off the contacts to the reservoirs. So I'm going to move to some full finite time description, but before that, I find it interesting to discuss the mechanism of pumping. And I have some animation. So the mechanism of pumping is very well represented by this Archimedes screw, in which you can rotate some spiral into this tube and pump, in this case, balls from one place to the other. It was proposed by Archimedes to pump water. And yeah, so this is pumping of balls against gravity, but I found it that recovering the topic of illustrating with animals, I also found this illustration where you can pump fishes along with water. Okay. Yeah, some of them don't survive, but okay, the mechanism is not perfect. Not perfect for the fishes. Okay. And okay, this actually has two operational modes. One is, well, the pumping I showed before. The other is the generator. You can use the water or the balls to rotate the screw inside the tube, and in this way generate work. So this is the classical illustration of the mechanism of pumping, and it was implemented some time ago with electrons. So this is an experiment that was done some time ago. So there is here a circuit with 3 capacitors. You can here apply a voltage difference, and you can also operate these islands between the capacitors with these gates and move these gates as a function of time. And this is the diagram that indicates the different charges of these 2 islands, this N1 and N2, as a function of the 2 gates applied there. And okay, what they show here in this experiment, this was also a proof of concept, that if you make some cyclic variation of these two gate voltages, making this circulation, you can pump 1 electron from this side to the other without applying any voltage. So you can let's say, move this gate, allow the charging of this island. You can close this gate. This island can move in this direction, and then move again this gate in order to make the electron circulate here, and it is tested. And okay, you can even work, it is not shown here, but you can even implement something like the Archimedes pump. You can put some gate voltage, and operating with these two gates, pump electrons against the direction imposed by the external voltage. So this is one experiment with the electrons, and that motivated some activity some time ago. It was quite inspiring. And this was a description of this kind of processes in terms of the scattering matrix approach. I'm going to say a few words in a while, but basically what they implement here is some adiabatic expansion in the scattering matrix. So I explained briefly the scattering, the formalism of the scattering matrix. I just gave some idea in the first lecture. You can make it time dependent, and you can expand it is in terms of a frozen part plus some adiabatic contribution. If you proceed that way, you get this expression for this is the current that you pumped as you modify two parameters in this system, like the two gate voltages I indicated before. So these X are these two changing parameters. What is interesting here is that you get here an expression that resembles a lot the definition of Berry curvature. So it is, okay, and this is an indication that this this mechanism of pumping can be described in terms of geometric quantities, and these were some other related papers. So actually, this one is very important because it allows to define topological invariance out of this pumping mechanism. So this is a geometric definition, but under some conditions it can be quantized. This charge can be quantized, and this corresponds to some topological case. This was precisely the case that was proposed by, and the idea that was put forward by Taules. Motivated by this work, there were some other experiments. This is one, and in this case, in terms, it is a much smaller system. There is a quantum dot here, and this quantum dot is connected to leads, so the quantum dot is this region, and it is operated by two gate voltages, which are oscillating with a given frequency and with the phase lag. And what you can measure, so this voltage difference is the voltage difference calculated, measured here, and these are basically proportional to the the current flowing there. And as you see, when these voltages oscillate out of phase, you can get some current. It is very difficult to predict the sign of this current. All you know is that the idea is that you, it's like you open a gate, some electron enters, you close the gate, open the other gate, the electron flows in the other direction, and you do it cyclically. So here is very important that it is done in this adiabatic regime, meaning that this frequency of the oscillation is very low. And this is precisely the range of validity of the formula I showed you before. So the description of these formulas, so the derivation of these formulas in terms of a scattering matrix, I'm going to say here a few more words, are like this. So this is the sketch I presented in the first lecture on how do you compute the scattering matrix in a problem. As I said, is pretty much the same as in basic quantum mechanics. You have some wave that it is injected from the left, and you basically calculate the probability of transmitting and reflecting it. But if you have this conductor here, this barrier oscillates with the given frequency, this omega, so if it has some periodic dependence, you can formulate this problem in the language of Floquet theory in a way that in each of these exchanges, so each of these reflections of transmissions, you absorb or emit one quantum, which is defined by the frequency of the driving. So the original steady state problem, stationary problem without any driving, defines you some scattering matrix, which is a function of the energy of the incoming particles, while in this case you will have to deal with some situation in which you have the energy of the incoming particle and the outgoing particle as well. So in this framework, in this language, you can implement also this adiabatic expansion I told you about in last lecture. You can decompose this thing, this scattering matrix, in terms of some frozen situation in which you freeze all your parameters at the given time, and you include some adiabatic correction. And this adiabatic correction in this language is proportional to the frequency of the driving. And it is the same as the velocities I was telling you about in the last lecture. So this formalism is good only for non-interacting systems. You can prove that it's equivalent to Green's function formalism, which can be extended also for some interacting problems. Okay, and this is some lectures, notes by Berry, and this is precisely to show that this is the definition of the Berry phase and the Berry curvature. So these are the geometrical phase that you get when you move cyclically your system in some parameter space. You see that the structure here, this is for the wave function, the original Berry phase is formulated for the wave function, but you get something which is pretty similar in this case for the scattering matrix. So this is the same geometric structure. So this connects to the motors. So the motors precisely are the quantum motors precisely connect, so are systems in which you take advantage of the pumping mechanism, and you operate them. So the Archimedes pump operates with some pumping, that some cyclic mechanism rotating the screw, and also with some with the gravity. So in this case, you don't have gravity, but you have you can put some electrical voltage. So you can have this electrical cyclic motion, and the electrical DC voltage, which plays the role of the gravity, and you can, for instance, these motors are similar to the generator, in which you take advantage of the pumping to get some electrical outcome, some electrical result in combination with the DC. And this is an example, this is a nice example because this case is a motor which is also topological. So imagine that you have this topological insulator that contains these two edge modes, and these two edge modes are perfectly conducting channels, but if you put them in contact to a magnet, the magnet opens a gap, so you don't have any conductance if you apply a voltage here because of the existence of of a gap generated by the contact with the magnet. It doesn't allow you any current along these two edge modes. However, if you take into account the rotation of the magnet, and you treat all this in a combined well, this works as a motor. So the magnet couples, so the magnetic moment of the magnet couples with the spins of the edge modes, and then you can pump electrons through the gap. In a situation where you expect not to have any current, you measure a current. And furthermore, this current you measure here is topological. So this is that every time the magnet makes a period, you can pump exactly one electron from this place to this other. So these are just for electrons, but the point is if we can implement this kind of mechanisms, I'm just giving some flavor of the idea, so I'm not providing the details of the calculations. Yeah, so the idea, if we can implement this idea of the motors, when you have some system, some quantum system that is operating under slow driving and in contact to two thermal baths at two different temperatures. And this is precisely the situation. We have here our quantum system, which is operated by time-dependent parameters, and we also have here a temperature difference. So you can even put some time dependency in the temperature difference, although I'm going to focus on a fixed temperature difference. And this is what we want to do. What we want is precisely to operate in this Archimedes-inspired way, in which you have a heat engine that corresponds to the generator mode. You have some heat flowing from the hot to the cold reservoir, and you can. The idea is to use this heat to produce some useful work. in combination with the driving. So the driving is represented by the rotation of the screw. And the other mechanism is that one. This is the Archimedes pump, in which you can use the driving to pump heat from the cold to the hot reservoir against the thermal bias. So all the time you will have some heat flux. So in a trivial situation, you will have a heat flux flowing from the hot reservoir to the cold reservoir, and you will also have dissipation because you are doing some driving. So you will have these two things. So you need some non-trivial effect, this heat work conversion mechanism in order to be able to get these green parts. So in a trivial situation, just implementing driving and connecting to two reservoirs, you cannot expect to have this heat engine or refrigerator. So this is something important. So the trivial processes are to have heat flowing from hot to cold and just dissipation. These are the two trivial processes that you should expect. Okay, so this is precisely what is indicated here. So as we have driving, we will have some power due to the driving, which will generate fluxes going into the left and right reservoir. But we also want to have some transport, some other components of the heat current at each reservoir that we call the transport component, which indicates the flow from one reservoir to the other. And this will contain the trivial heat flux, and eventually, if we are able to implement a good heat work conversion mechanism, we'll have something else that will allow us to implement the heat engine or refrigerator operational modes. So these are the conditions in which we are going to work. We are going to focus on slow driving, so these velocities will be small, so basically the same story as in the previous lecture, and small temperature differences, so linear response in delta T. So here, if we want to implement some Kubo description, as I explained in the last lecture, we have a problem because because we have a temperature difference, and the temperature difference cannot be represented a priori in a Hamiltonian. But there is a trick in that works in linear response that was proposed by Latinger, the same as Latinger liquids. And it was to add to the Hamiltonian some term that represents the temperature difference. So this term is to include in a gauge field in a similar way as you include in a gauge fields the voltage difference in Kubo formalism. And this was an idea, quite old idea, as you see. And there are some further elaborations of these ideas. Basically, the additional term you add is the heat current, the energy current in this case, times some gauge potential, such that some time-dependent gauge potential such that the derivative in time of the gauge potential is equal to the temperature difference. So you see that it's very convenient to combine with the adiabatic linear response, because this can play the role of a small velocity, so we can also combine with all the other parameters. There are some technical details that one should be careful about. There are some terms that may appear that are explicitly dependent on this additional potential you are adding, that you should make sure that they are cancelled, and these are some details to have care, but it's basically the same linear response that I explained in the previous lecture. So now then we have this in the usual adiabatic linear response. You have these quantities that I gave the name of forces, and this take into account the derivatives. They are defined as the derivatives of the Hamiltonian with respect to the driving parameters, and we can define a sort of superforce operator in which we have the all forces associated to the change to the driving parameters, and this extra quantity that is added in the Latinger because of the Latinger description. Okay, so this is recall. So now this adiabatic linear response, which will look like this at the end after performing all the Kubo-like expansions. We will have some susceptibilities associated to the velocities due to the driving parameters, and the extra susceptibility taking into account this temperature difference. Okay, so the procedure is the same, so all this is formal at the end. We will get for the forces some frozen component times some component. This was the component we wrote in the last lecture, and now we are going to have this additional linear response coefficient, which is proportional to the temperature difference. And in a similar way, for the heat current, we also have some response due to the, so this, we have n time-dependent parameters. The n plus 1 is associated to the temperature difference. And this is then the heat current, which contains a term which is a response to the driving parameters, and we also have the response to the temperature difference. So this component here is the trivial one. So this is basically the thermal conductance that tells us that if we have some temperature difference, we have some heat current. And similarly, this, it will appear soon, this part will be related to dissipation. So the interesting part are these crossed terms. And as these quantities are derived in this linear response framework, and they are evaluated with respect to some frozen equilibrium Hamiltonian. They obey micro-reversibility, and they are basically the same as the usual Onsager coefficients. So they are Onsager coefficients. And because of that, they satisfy Onsager relations. So this is what we know that Onsager relations should satisfy in the presence of a magnetic field. What is not easy is to predict for an equal magnetic field, which is the relation between the cross parameters, the 1, 2, and the 2, 1 at the same field. So it depends a lot on the characteristic of the system, and the symmetries also play a role there. In many examples, these are symmetric for the part of the driving parameters, but I mentioned in last lectures that there are some cases in which you can also have some antisymmetric component for that, but for the most usual cases, these coefficients are symmetric, while also for the most usual cases, these other, which relate the responses to the temperature difference with the driving, are anti-symmetric. So this is something that I think is not completely understood. It also depends a lot on the details of the system under investigation. So now some notation for the part associated to the driving parameters. I will define this matrix denoted in this way with some underline here, while with the others which connect the heat current with the driving parameters, I will define a vector, and the other will remain alone. That is the usual thermal conductivity. Okay, so let's see, given this notation, how does the work and the heat look like? How do the work and the heat look like? So this is the total expression of the work, in which I'm defining it in a way that it is positive if you get something out. Otherwise, if you get dissipation, is negative. And you have here the dissipative part. So this is the one I mentioned in the previous lecture. But now we have this component here, which is the response to the response in the driving forces to the temperature difference, and this quantity describes pumping, and I'll show you why. This quantity describes pumping, and it is a geometric quantity. So you see that you can express this as a line integral in the parameter space. So this is a geometric quantity that resembles the Berry phase, and it describes pump because of the following. You get this expression for the transported heat current, for the transported heat. So this is integrated over a cycle. So over a cycle, the heat you transport between the two reservoirs has two components. One, which is the trivial component, which is this one. You have here the thermal conductance and the difference of temperature, but you have this one. And if you don't have any temperature difference here, if you put this delta T equal to 0, you see that we still have this component. So this is precisely the component that describes the pumping, that you don't need any temperature difference to have heat transported from the two reservoirs. It is just a response to the driving parameters in your system. And it is exactly the same quantity, so they are, all these processes are related to, by Onsager, relations of these coefficients. And yeah, what we see here is that this pumping is precisely the term that generates this heat work conversion. So you see that we have dissipation, which is always negative, but if this component can have any sign, so you can pump heat in both directions. If you have if this pumps heat from the hot reservoir to the cold reservoir, you can compensate the dissipation and you get some useful energy, some useful work output here, thanks to the existence of this term. So this is like the Seebeck and Peltier coefficients in thermoelectricity, but at the level of a system in which you have driving. And yeah, so this is the other operational mode. It is the refrigerator. In the case of the refrigerator, you expect to inject some extra work, but you expect to have some heat that is extracted from the cold reservoir. And you see that if this pumping here component has a negative sign, you can extract heat from the cold reservoir and inject into the hot one. And this is precisely the mechanism similar to Archimedes' screw. So some highlight here. It is notice that the expression that I presented in the first slide for the Carnot cycle was that in the Carnot machine, we had that the work, I said this is the heat work conversion. The work is the heat extracted from the hot reservoir for the case of the heat engine times the difference of temperature divided by T. So here we also have something like that, but it's not coming alone. So this term is coming, so this is basically this term. This term is coming along with the with dissipation. So you somehow recover in the limit of vanishing dissipation the Carnot, the result of a Carnot machine. And the other thing is that this pumping, component has the structure of, has a geometric structure. I already mentioned that you can express in terms of this line integral. So an important take-home message here is that in order to have this integral different from 0, you need at least 2 driving parameters. So if you have just one parameter changing in time, you won't get any thermal machine, at least working at slow driving. So because this, yeah, if you have just one parameter, you will have something which is you go in one direction, you go in the other direction, and the line integral will give you exactly 0, right? Yeah, some example. So, are there questions? Okay, I can move on the example. So, this is an example in which the simplest example you can figure out is the case of a single qubit coupled to two reservoirs at 2 different temperatures and driven by 2 time-dependent parameters, this Bx and Bz. And the idea is to perform a cycle with this time dependence of these B's there. So the reservoirs are caldera-Leggett-like reservoirs, a set of harmonic oscillators, sorry. Yeah, what you want here is to do some, I mean, to get some non-vanishing value of this line integral is not that easy. If you do any protocol, you will get a vanishing value. Of course, with a single parameter, you will get a vanishing value. But with 2 parameters, you have to be somehow careful because you can do something in half of the cycle and undo it in the other half of the cycle. It's similar to the case of the thermoelectric coefficients that you have electrons moving in one direction and holes moving in the other direction, and you compensate the current generation in thermoelectricity. Here it happens the same. So in order to get that, it is important to introduce some asymmetries here. So in the case of thermoelectricity, you implemented some mechanism of particle-hole symmetry breaking. In this case, we need some mechanism of implementing some symmetry breaking in the device, and the mechanism is by connecting with different Pauli matrices the qubits. So with one of the reservoirs, I connect with sigma x, and with the other reservoir with the sigma z. And okay, so in this example, the solution was obtained. So for the results, so the calculations were done in this master equation. Is not exactly the usual Lindbladian equation, but it has a similar structure. You can write down some master equation, assuming that these couplings are very weak. And this takes also into account the fact that you are coupled in different ways to the 2 reservoirs. And okay, I explained last time how to calculate the work done by the forces when you have driving. You can, within this formalism, calculate the heat flowing between the 2 reservoirs, and it is given by the Hamiltonian times the Lindbladian part, the trace of that. And okay, you have some frozen component and some adiabatic component, as in the case of the dissipation. And these are some results. These are the results for this vector I defined, and this is for the different protocols. And there you can, in this representation, quite easily visualize that, and for some protocols you get a vanishing value of this line integral, and for some of them you get a finite value. So this is the some results. So the protocol here is very simple. These are basically ellipses. So you have the same driving frequencies centered at some given point of the parameter space, and these two components oscillate with the same frequency and with the phase lag in a similar way as the gate voltages. Yeah, so this is the results. So the result for this pumped heat from between the two reservoirs, this is without any temperature difference, is a function of the phase lag, which resembles a lot the problem of the electron pump with a very similar protocol. And okay, so this is a sketch on how to understand this protocol. Imagine that, so how to make it work so once you verify that you have this pumping component, you know that it can work as a motor, or as a heat engine or a refrigerator. And this is the way it works. Imagine that you start at some part of the protocol in a situation where your state, the state of your spin, is oriented in a direction that is connected to the cold reservoir, but not connected to the hot one. So as I said, it was coupled with different types of coupling between the two reservoirs. So you can have a heat which is flowing from the cold reservoir into the two level system. Then you let the space, the energy space between the two levels evolve in time till you arrive some situation in which you fully couple to the hot reservoir. So you deliver the heat, the energy you collected in the first part of the cycle, and you continue the cycle, but in an asymmetric way, so that you don't. So you end in the same situation, but not undoing what you have gained. So this is an easy way to think about that. And in fact, you can calculate that in this kind of protocol, you are able to transport heat from one place to the other. It is so these geometric descriptions are interesting because we have some geometric description for the transported heat, and we also have some geometric description for the dissipation. So these two things can be combined, and I'm going to briefly tell you about that. So these are the same expressions I showed you before for the work and for the heat. We have here this pumped component, which I expressed before as a line integral, but it can be using Stokes' theorem expressed as an area integral. Because of that, we called it area. And we have this dissipation, which can be related to the thermodynamic length. So it can be bounded by the thermodynamic length. And we have this heat conductance. But these two, so this is not geometrical, but these two are geometrical. And yeah, it can be, so it's possible to define for the for the operation, the power. So let's focus on the heat engine operator, in which you want to get some power, and given, so the efficiency is always what you gain divided what you have to invest. What you gain is work, what you have to invest is heat. These are basically rephrasing of the, so some definitions in terms of the original definitions I introduced before. And it is possible to implement some, so to optimize the duration of the cycle in order to get a maximum power or a maximum efficiency. And what is nice here is in the optimized power, you get this ratio. And this ratio is a ratio of what we interpreted as area divided by what interpreted as length. So, but the length is a length defined in some strange metric in this parametric space. And this area is this area, which is, yeah, this is an area, but this weight with this very connection. Yeah, so, and we found that this unsolved problem in math. So in geometry, people are still investigating. There are plenty of works devoted to investigate precisely this problem, optimizing the ratio between an area and a length in a space where you don't have an Euclidean metric. So we know that in the Euclidean metric it is a circle, but in general it is still a problem that people are studying. So these are the protocols. So you have this map for this for this very curvature, and it looks like this in this particular problem. And you see that it's very easy in this representation to define which are the optimal protocols regarding the optimization of the area, or the optimization of the area means optimization of the particle, of the pumping, sorry, of the pumping. So in particular, it's easy to see that the super optimal protocol will be some protocol in which there is still an error in the arrow. So in some protocol that covers all this quadrant will give the optimal, so the maximum value for the pumping. And this saturates in these numbers that is known by the Landauer bound. So it's the maximum, it's related to the maximum entropy that you can do to generate a change in a spin, in a two-level system. It is anyway some protocol that will be achieved at very long periods, because you have to cover all this sector. But yeah, given that optimal protocols for the area, you can play with different forms in order to get which are the ones which are also optimal for dissipation, and this means minimizing the thermodynamic length. So in order to minimize this quantity, you have to, instead of circulating around the the protocol at the same velocity, you have to adjust the velocity in order to have a constant dissipation point by point. Okay, so these are the results, but this is the nice thing is that these geometric representations are very useful for optimizing protocols. So I'm basically finishing, so I would like to mention you some still, I think, open, interesting problems related with this geometrical story. The first one I already commented is related to the connection with the topology. So we already have something which is geometrical. Under which conditions can we design protocols that are also topological? So they are not only geometrical, but they are quantized or related to some quantized quantity. There are already studies in that this direction, but not yet at the level of the heat exchange, but only at the level of the power exchange. So this is one thing, and the other thing that I think is still interesting is to study the spin boson problem out of equilibrium. So all these results I showed, and most of the results done for the qubits, are in the limit of extremely weak coupling between the two-level system and the reservoir and all these Lindbladian descriptions and so on. But there are experiments in superconducting circuits where the qubits are studied in the regime of strong coupling with the circuit. The circuit is precisely which plays the role of the invariant of the environment. And the spin boson problem is an important problem which shows a phase transition and out of equilibrium and with different type of couplings and so on. It's a zero-dimensional problem, but it has but not non-trivial. And I think that there are things to be done here. So this is just a recent review article where you can find plenty of references with focus on the qubits. But well, so this is the take-home message of today. So these quantum systems operating under periodic driving in contact to two or maybe more thermal reservoirs at different temperatures may operate as thermal machines, engines, and refrigerators, but this is if and only if there exists some heat work conversion mechanism. So you can find in the recent literature many articles when there is some driving and some contact to reservoirs, and they call these heat engines, but driving doesn't guarantee being a heat engine or a refrigerator. You need to really identify these heat work conversion terms. And yeah, in this limit of slow driving, you can identify this heat work conversion term and describe it as a geometric quantity which has a structure similar to a very phase, and is very useful to combine with protocols that minimize dissipation through the concept of the thermodynamic length. So as this is my last lecture, I'm going to leave you. I would like to acknowledge the work with several people collaborators, students, and also collaborators abroad. So these are my students now. This is a list of ex-students, recent ex-students and postdocs with whom I have been working in this subject. We had some collaboration with an experimental group in the problem of thermoelectricity. We have some fun results there. These are colleagues from Argentina, from Bariloche. People, so I organized more or less randomly people from, okay, Eduardo from Urbana, Alfredo from Madrid, David and Rosa for Balears, also Martí from Geneva, and Janine from Chalmers. Colleagues from Pisa, and yeah, very especially I would like to thank Misha Moskalets, who had to escape from Kharkiv very recently, Saro, who was around, and Felix von Open. I received some support from Argentina, and also I would like to thank the support from Alexander von Humboldt Foundation. And yeah, that's it. So you have my contact there, and please write me if you have ideas, questions, whatever. This is a very nice picture from an artist from Argentina. So thank you very much.